Hey, welcome. Today we're going to be talking about how to work with the mirror equation and how to work with the magnification equation for physics classes for curved mirrors, for concave and convex mirrors. First we'll define some variables, then I'll show you 4 different examples. I'll also show you the common errors to avoid. So let's go ahead and get to it. First of all, this is the mirror or the lens equation, depending on what you're working with. So it's 1 over the focal length is equal to 1 over the distance to the object. That would be the distance from the mirror, in this case, to the object. It's usually going to be written as d sub o. You can also see that as a p value. And then the next term is 1 over di. That's the distance to the image, so the distance between the mirror and the image itself. It can also be written as q. And the way to remember that is p comes before q in the alphabet. Alright, now there is the magnification equation as well. So the only thing that's different here that you haven't seen before is hi and ho. H sub I stands for the height of the image, and H sub O stands for the height of the object. Alright, let's see how to apply these things with a few different problems. So this first problem, we're going to say a burning candle is at a distance of 3.2 centimeters from the spherical concave mirror, and the image is 3.7 centimeters from the back side of the mirror. What is the focal length of this mirror? So we're going to start with our mirror equation up top here, and we can also draw our ray diagrams. So I've done a screencast on how to draw ray diagrams for mirrors. I'll put a link to that in the upper right about now, but I'm also going to demonstrate it here. So the very first rule is if a ray comes in parallel to the optical axis, it'll bounce out through the focal point. So let's go ahead and draw that. The second rule is if a ray comes in through the focal point, then it's going to bounce out parallel to the optical axis, so the inverse of that previous rule. Now in this case, if we start from the top of the object right here and go down, it's never going to intersect with this curved mirror over here, so instead we draw it as if it had come from the focal point. So as if it had come from the focal point, so it's going to head off at this angle right here, and after it does, it's going to bounce parallel to the optical axis on its way back. Now I could ask a trick question on the left side of the mirror, where are these two rays going to intersect? And you could say, well, nowhere, or they are diverging, or they will never intersect on the left side of the mirror. So what our brain does is it traces this image back to see where it appears to be coming from. And this is the mistake that students usually make when they draw ray diagrams. You could label these as like a 1, 2, 3, and 4 right here, and they will trace back the wrong rays sometimes. So you want to trace back the rays that have already interacted with the mirror or the lens. In this case, that would be this ray right here and this ray down below here. So you're going to trace those back, and where they intersect is where the top of the image appears to be. And so that's a quick rundown of how to draw the ray diagram here. Alright, so now let's use the math. Now let's use the equation, the mirror equation. So we're going to go ahead and plug in our numbers. And I want to show you one other issue where students oftentimes make a mistake, and that is here. So if you convert from a fraction to a decimal, and then you combine your terms like we do over here, the answer is not 0.042 centimeters, and that's the common error that students typically make. What we need to do is to still take the reciprocal or the inverse of this fraction on both sides, and so we end up with the focal length is going to be 24 centimeters. So that's how you do the first problem. Let's take a look at the follow-up. So this is 1b. What is the magnification of this image for the same problem? So if you want to pause for a sec and work it out yourself and see how you do, go for it right about now. Alright, so next we need to figure out what 2 out of the 3 parts of this equation we're going to use. We don't have any information about hi and ho right now. We do have information about di and do, so let's go ahead and use this and this, and we can just ignore this part of the equation for now. So we're going to go ahead and do that. We plug in our numbers, we end up with 1.16. Notice this is a unitless answer, and what that means is it's a ratio of the height of the image over the height of the object. I think this is the easiest way to think about it. So what this is telling us is the image is going to be 16% larger than the object was. Alright, so let's see how to apply this in another case. This is going to be a convex mirror situation. What is the image distance? So I do want you to take a moment to see if you can figure this out, if you so choose. If you want to pause it right now, now is a good time. Alright, so the very first thing we need to do is to draw our ray diagrams. If the ray comes in parallel to the optical axis, it's going to bounce out through the focal point. That is impossible here since it is a mirror, so the ray is going to bounce back as if it had gone through the focal point, like right here. Second rule is if a ray comes in through the focal point, it's going to bounce back as if it is parallel. So we start like this. Notice it is a mirror, so it must bounce back. And so it's going to bounce back as if the first ray had gone through the focal point. So it bounces back like that. Now, which of the 4 rays that you can sort of think about here, 1, 2, 3, and 4, should you trace back? Because these 2 rays are never going to converge. So our brain traces these rays back to see where they appear to be converging. So which of the 4 rays would you trace back? Again, we would trace back rays 1 and 4. So if we trace those 2 rays back, because 1 and 4 have already interacted with the mirror, so you need to trace the rays back that have already interacted with the mirror or the lens if you need to trace rays back. And so that's where our image is going to be. What is the image distance in terms of the math? We go ahead and start with this equation over here, and we're going to isolate for di eventually. So I'm starting to get di by itself, and we want to convert from our fractions to our decimals, combine those terms, take the inverse or the reciprocal at the ends, and you end up with this as your answer. Notice this is a negative answer, and what that means is it's going to be behind the mirror. So for mirrors, the image being on the front side is kind of like our default, and you can think of it as being a positive di. And if our image is behind the mirror, that's going to be treated as a negative di. So default for mirrors, we assume the image forms on the front side of the mirror. That is the opposite for lenses. For lenses, we assume that the default, so to speak, is going to be on the back side of the mirror. Alright, so the next follow-up problem we have is what is the magnification of the image? If you want to stop right now and do the math, go for it. But it's pretty straightforward. You just go ahead and plug in the values that you have, and notice that it's going to be 0.59 as our answer. That means the image is about 60% in terms of the height compared to the height of the object. By the way, ray diagrams are a great way to check if you are doing things correctly. You are probably not going to be drawing them to scale. If you did, they should turn out to be perfect. Most people are not going to be doing that. They're just going to draw like a ballpark answer to double check their work or to demonstrate what's going on or to understand what's going on. So, speaking of understanding what's going on, hopefully that was helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.